Hello everybody and welcome to this iFormulate webinar on particle engineering using spray drying and fluid beds, which we're running in association with the University of Leeds. In this webinar we wanted to give you a brief overview of iFormulate. To start with, the company was founded by David Calvert and myself, Jim Bullock, and between us we have well over 60 years experience working in the formulating industries. We've been in business for over 7 years now together and have experience and knowledge gained across many industries and in varied functional roles. And we also work together with associate partners whose expertise we can combine with our own and assist our clients as effectively as possible. We divide our activities into 3 business areas. In iFormulate Consult, we carry out innovation and technology consulting, mainly in formulation technology for client companies in private sector industry, and that's the majority of our business. In iFormulate Strategic, we've carried out and assisted strategic projects in the area of formulation for industry organisations such as the UK's Knowledge Transfer Network, the UK's National Formulation Centre, and the Royal Society of Chemistry. And under iFormulate Skills, we design, deliver and promote training courses and programs in formulation science and technology under our own banner or in partnership with third parties. So my name is Jim Bullock from iFormulate and I'm joined today by Professor David York from the University of Leeds. Since 2012, David has been Chair of Structured Particulate Products in the Department of Chemical Engineering at the University of Leeds, and he previously held senior roles in process development and product development at P&G. And this webinar is designed as an introduction into the basics underpinning the processes of spray drying and fluid bed in terms of particle engineering, as well as the implications for the options you've got for design and operation. Now, the overview, I'll start by covering particle engineering using spray drying. David will move on to discuss particle engineering using fluid bed, and we'll wrap up with some ways to learn more and a brief question and answer session. The webinar will last around 40 minutes and it's being recorded, so it will be made available to participants afterwards, both the recording and the slides. If you'd like to ask questions, then you'll see on your GoToWebinar panel a question box, which you're welcome to use, and we'll try to answer those at the end. You're all muted to prevent any background noise, and we look forward to hearing questions at the end. So first of all, what is particle engineering, in case some of you aren't familiar with the term? Here's my definition, at least. Particle engineering is really about making particles with the right shape, size, structure and surfaces to give you the product properties that you want. And today we're going to be talking about 2 alternative ways to engineer particles: spray drying and fluid bed processing. So let's go through the basic principles of spray drying first. In spray drying, you start with a fluid feed, which can be a solution, an emulsion or a suspension in water or alternatively other solvents. And this is pumped through an atomizer nozzle to form droplets. You can actually get away with quite a wide range of viscosities as long as it can be pumped through and through the atomizer to form those droplets. That's all you need to be able to do. Sometimes the pressure needs to be quite high, but a wide range of viscosity for that fluid is possible. Those droplets enter the spray drying chamber or tower together with a separate stream of heated gas, which is usually air, but not always. As the droplets fall to the base of the drying chamber, they're dried by that hot air, and as they dry, they form solid particles. So the idea is that by the time they reach the base, those droplets are dry, solid particles. Those particles are then removed and separated using things like a bag filter or cyclone system. Spray drying is a rapid and efficient process due to the very high specific area of those very fine droplets. And that high specific area allows a rapid heat transfer and mass transfer. And that last point's important because drying actually happens at the interface between the droplet and the hot air. So that surface area is critical to the speed of drying. When you atomize to form small droplets, you're creating surface area, But more surface area means a higher surface energy because of surface tension. Therefore, you do need to put in energy to do that atomization. That's why you normally need to apply pressure to your fluid through the atomizer. Let's have a look at one configuration for spray drying. This is the co-current spray drying system. There are many variants, but this is a very common one. In the co-current system, liquid is atomized here. You can see the liquid feed passing through the atomizer here at the top of the vertical tower. These droplets fall by gravity through the tower. The hot air in a co-current system comes in close by, so the hot gas feed is also fed in at the top of the tower, and at the bottom of the tower your particles exit, and also the hot humid air which has been formed from the drying also exits. Big dry particles are quite easily separated from the hot air. Finer particles can be separated by cyclone, and dust is removed in filters. So what sorts of particle engineering options might you have using spray drying? First of all, size and controlling size. The primary effect on size is the droplet size, and the droplet size is controlled by the atomizer and atomization conditions. But you've got to consider here, will any big particles be dry by the time they reach the bottom? If not, and you want big particles and big droplets, that might mean that you need a taller dryer. So size is important. Shape then, the droplet is usually spherical, so we'd expect the particle to be spherical too. This is often the case, but not always, and that depends on the drying conditions, as we will see later. And then structure. We can build internal structure, for instance core shell structure, using spray drying, or an external structure by agglomerating particles together to form granules. And as a result of engineering the particle, we can influence and enhance the product properties. So for instance, we can make a granule strong such that it doesn't break down to form a dust, or we can encapsulate an active component to control its release properties, or we can make a solid flow better by altering particle size, shape and smoothness. Or we can make it redisperse better in water, for instance, by altering its size, its shape or its density. Let's have a look in more detail about what happens to droplets in a spray dryer. And we'll start the journey on the left-hand side. Here's the droplet. And at the start of its journey through the spray dryer, the droplet has a uniform water content, and the surface is saturated with water or the solvent. Now here the drying takes place from the surface of the droplet, assuming the water can get there fast enough. The air here outside the droplet is hotter than the droplet, and initially all of the heat goes into evaporation of the water and not by heating the droplet. And as long as the relative humidity around the droplet is low, there's a driving force for that drying process to happen. Over time, let's move on to what happens after a little bit of time here. Once water transfer from the center stops, the surface water level decreases. So the surface is no longer saturated and the crust can begin to form around the outside of the particle. And this can happen for water moving from the inside is not coping with the demand from evaporation. So it's actually too slow to move from the outside, and the outside is no longer saturated. Transfer of water, and this is where size is important here, because transfer of water takes a finite time. So bigger droplets will have a bigger difference in water content between the core and the surface. This is also where material properties of the formulation becomes important. So if your solute bonds to water, for instance things like surfactants or starch as your solvent, this can limit the rate of water moving through the droplet, so the temperature rises. And in some cases water transfer becomes so low that it turns to steam inside the droplet, causing rapid expansion, blowing a hole in the particle and making porous material. So what happens in these latter stages is really very much dependent on the material properties of the droplet and the details of the drying conditions. So another word on the importance of the droplet size, and as we've seen, smaller droplets will dry faster due to a higher surface area. The water also has less distance to get to the surface. So these diffusion and particle heating effects that we've talked about are less likely to happen for small spherical particles, and you're more likely to end up with uniform, smooth spheres. With bigger droplets, as we've seen, there's the chance of larger water gradients forming. So bigger droplets will take longer to dry, but they do fall faster in the tower, and that's the reason you might need a very tall tower to get your droplets dry. But although you might want big particles for low dust or for good flow properties, there's going to be a limit then to that maximum droplet size. And you might have to settle for spraying smaller droplets and making smaller particles, and then agglomerating them either in the tower or afterwards in something like a fluid bed. And there'll be a little bit more on that in a moment. Now, so far we haven't said too much about the atomizer, or the atomizers that can be used to make the droplets. Now, there is a lot of choice and a lot of different atomizer designs. An atomizer design is a big topic in its own right, so I'm going to be just very, very brief here. But very briefly, you can atomize by use of a spinning disc, and that sprays tangentially in the tower, and the tower for that reason is relatively short and wide. In a spray atomizer, a nozzle atomizer, you might choose a tall and thinner tower for longer residence time. So let's go back to that co-current design with the heat and the atomization at the top. This is the much more common design. Both the fluid and the drying gas follow the same direction through the tower. Very often you're dealing with a lower viscosity fluid here and creating spherical particles. As we said, you're creating a relatively fine powder, 100 to 200 microns in diameter. Now, an advantage of this kind of design is that you've got fine particles that dry relatively quickly. So you've got rapid drying, a low time in the dryer, and relatively hot and wet conditions. You're getting all of that energy going into drying the droplet and not heating the particle up. And so it can be used for temperature sensitive products. And you can use it also for high water content products with little resistance to internal diffusion. Let's move on to engineering the particle shape, and there are many possible morphologies here. We've mentioned small droplets becoming small spheres, and as we've said, larger droplets may blow open. So if the material is rigid, the droplet or the particle may more or less retain its spherical shape when blown, just with a hole in it. But if the material is flexible, the sphere may collapse once it's blown open, and you might get that kind of squashed raisin shape or squashed football shape that's quite often seen. If the material is more brittle, then when it's blown open, the sphere can actually fracture, forming a dust. We'll come on to hollow spheres, encapsulates and agglomerates in a moment, but just to stress the importance here of understanding the material properties, the process conditions, and the equipment factors. And ideally what you want to do is work out in advance what kind of shape you want, and then work back to optimize the formulation or the process conditions. So as promised, a short word here on shell formation. And in spray drying, a useful concept is the Peclet number. And the Peclet number is defined as the ratio of the rate of evaporation of solvent to the rate of diffusion of the solute. So for low Peclet number solutes, these diffuse faster than the droplet can shrink, and therefore the solute can move to form a small solid sphere like this as the water is lost or the solvent is lost. For high Peclet number solutes, These solutes diffuse slower than the droplet can evaporate. So the evaporation is happening more quickly than the diffusion rate. The solute kind of gets left behind as the water is lost, and a hollow shell particle can be formed. Now these are the extremes of morphology, and there are a lot of other possible morphologies that are possible. And I've included here a couple of references if you're interested in going to more detail about particulate numbers and about drying conditions and material properties and morphology, if you want to follow those up. Let's talk here about microencapsulation and more complex structures that can be formed within the spray-dried particle. So maybe you want to encapsulate a volatile oil, a fragrance or a flavor, for instance, within a solid particle. Here your fluid feedstock will be an emulsion of that oil in water, for instance, and included in that feed will be other materials such as starch or a protein, as well as a filler polymer on top of that as well. So that's on the left-hand side here. You can see our droplet, our water droplet that is atomized, containing within it an emulsion of oil droplets and dissolved starch and filler. Let's just zoom in on one of those droplets and have a look at the oil droplet itself. Starch migrates to the oil-water interface. To some extent it's surface active, and as the drying particle gets hotter, starch can sinter to form a coating around the droplet to encapsulate that oil droplet. And on the right hand side you can see what the final particle will look like. Essentially it will consist of oil droplets surrounded by that solid starch coating, all embedded in the filler polymer. And that's actually quite a potentially cost-effective approach to encapsulation compared with other methods such as interfacial polymerization. So earlier I promised to mention agglomeration of particles, and one way of doing that is in the spray drying tower itself, and here you would need probably a countercurrent design of spray dryer. And in a countercurrent spray dryer, the product fluid enters at the top, but the hot air, the drying gas, flows up from below. And that means that the greatest driving force for drying is where that hot air is hottest, and that's at the bottom of the tower. By creating circulation forces for the droplets in the tower, you can get those droplets to collide with each other and to agglomerate as they dry in the tower. And the tower design needs to be such to extend the residence time and to maximize the probability of collisions of particles. You also need to be careful about your materials properties so that the particles adhere to each other and don't bounce off each other when they collide. And using countercurrent granulation and agglomeration, you can get to higher particle sizes up to over half a millimeter in size. Very often used for detergents and slower drying slurries, and you can make here from these sorts of materials quite low density porous products that will redisperse very nicely in water, for instance, after on use. And here's a schematic of a countercurrent dryer. Just wanted to point out the differences here. Here again is your liquid inlet and atomization into the tower at the top. The difference here being that you've actually got hot air coming in the bottom, and here in the middle of the tower is where you get the drying and the agglomeration, and then you get feed of the larger particles out of the bottom of the tower as before. Another method of agglomeration is by following the spray drying step with a fluid bed at the base of the spray drying tower, and David's going to talk in a moment about fluid bed in much more detail. The design in this case is usually a co-current spray dryer, and that will have produced, as we've seen, primary particles which are typically pretty fine and spherical, and these can then be agglomerated in a second step using a fluid bed after the spray drying step. So let's just run briefly through the pros and cons of spray drying before moving on to fluid bed. The advantages: It's a very rapid drying process due to that large surface area and very good contact between the droplet and the hot air. You've got a high mass and heat transfer as a consequence. It's a semi-continuous process in a single stage. It's pretty flexible, therefore, and reduces the amount of handling of product that you need to do. If you get your conditions right, the heat can be used to vaporize the solvent and not heat the solid very much, so it's got potential for use for sensitive materials. And it's a very good method simply of drying. It's a very efficient way of removing water at the end of a formulation or a synthesis process, which might have given you a formulation with too much water in, and you want to get a dry product out of it. So it's simply as a method of drying, it's useful. It's got high potential for particle engineering, as we've seen, and we can change things like size, morphology, agglomeration, and encapsulation. Disadvantages: well, the equipment can be large and complex and expensive. It must be you must be able to pump and atomize that starting suspension, solution, or emulsion. So there's got to be a pumpable feed to start with. And as we've seen, you need to understand the properties of your formulation and your material, as well as your process conditions, to control that properly for optimum results. And for that reason, also, the scale-up may require some care. So now, before we move on to fluid bed, I'm just going to unmute David and hand over to David York to talk about particle engineering with fluid beds. David.
Thanks, Jim. Fluidized beds and spray dryers have things that are in common, in the sense that you're dealing with surfaces that are of particles or droplets, which are very small, and consequently you can get a very high surface area to volume ratio, which allows you to do lots of things more efficiently, because you can increase the high, you can have high heat and mass transfer coefficients. One of the two differences is that spray dryers are limited in time, as Jim mentioned, because you basically have a droplet which falls under gravity from the top of the bed tower down to the bottom. So there's a time limitation. And you can see when I describe fluid beds that time limitation disappears with fluid beds. So that's a difference between the two. The other difference that's important is that spray dryers start off with a liquid drop and form the particle as it dries. Fluid beds require a particle already to exist, either as a solid or a semi-solid, onto which you can do lots of different transformations, so that often you will have a fluid bed at the end of a spray drying tower, in order to the way the spray dryer produces the solid particles, which then go into the fluid bed, and we'll talk a bit more about that. But basically, as I said, fluid beds have to start with a bed of particles, and that bed of particles is basically a static bed. And what you do is you pass a gas, typically air, up through the particles, through the pores in the particles, and as the gas flows across those particles, a pressure drop occurs, which is due to the resistance in flow of the gas caused by the size of the particles. As you increase that flow rate of the gas, the pressure drop starts to increase, and you get to a stage where that pressure drop is equal to the pull of gravity on the particles, and they basically escape gravity and become fluid-like. Increasing the fluid rate, the gas rate any more, just increases the amount of turbulence in the system, but will not increase the pressure drop. And as long as that gas flow rate is maintained, the fluid bed is maintained. Let's have a look at a quick diagram as to what that looks like. On the left-hand side, you can see a static bed. The surface is fairly rough and uneven, and there's no movement of the particles. But you can see that there's a porosity of the bed. There's gaps between the particles that the air can flow through. And as you start to flow the air through upwards, nothing much happens for a while except the pressure drop increases. And then all of a sudden, you will fluidize. You'll come to the minimum state of fluidization, and the surface of the bed will go level, horizontal, and it'll start to behave like a fluid, like a liquid. And you could view these things as basically huge molecule-like liquids, where the particles start to move around. And as you increase the flow rate, those particles move around from side to side, up and down, and you get very good mixing of the particles and very good interaction between the air and the fluid. So that's a very simplified view of what's going on in the bed. The next slide talks about the properties of fluid beds. So there is a defined pressure drop across the height of the bed, and that's dependent upon how high the bed is and the nature of the particles that you've got in the bed, how heavy the particles are and what sort of shape and porosity. Won't say too much more about that, but we cover that in the course Jim's going to mention later. One of the advantages, though, is you have lots of movement in random directions, and you have like a bubbling surface, so you like a pan of water, and so you get lots of mixing and lots of interaction between the gas and the particles. So you have lots of particle-particle interactions and lots of gas-particle interactions, and so you can do lots of interesting chemistry onto the surface and physical transformations because of that excellent heat and mass transfer. So the point here, though, around time is that you can have very long residence times in your bed because it's maintained by the gas flow rate rather than the height of a tower with respect to gravity. So it gives you opportunities of drying at much lower temperatures over longer periods of time. So on the next slide, we can see how those properties drive the use of fluidized beds. And there are many different uses of fluidized beds, and a lot of those that we cover in the course. The first one is because of that good mass transfer, you've got lots of gas hitting the surfaces of the particles. And so they're very good for heterogeneous reactions. So coal power stations typically will use a very fine pulverized fuel of coal, which ground very fine and then fluidized, and so you have a huge surface area, and you pump in oxygen in the form of air, and you can get very high reaction rates, lots of energy created in a very small space. So power stations tend to use fluidized beds because they're much more efficient because of that very high surface area. The surface area is also used for where the particles, instead of being burnt, those particles are heterogeneous catalysts, where you have typically porous particles where the surface is coated with catalysts, and these move around and you pump your gas through them. So instead of burning them with air, you put hydrocarbon gases through, and they crack under the conditions of the catalytic reactor, and so you can get very good and efficient reformations of hydrocarbons in these systems. Fluidized beds are also very good at drying. You get very good heat transfer like you do in a spray drying tower, but you also then have the benefit of a large time window. So you can dry particles over a long period of time and at a lower temperature, particularly useful for temperature sensitive materials. Also sometimes used at the back of spray drying processes to increase the capacity of a system, whereby you only partially dry your particles in the spray dryer to form a particle which is can be moved about in a fluid bed, and then you can increase the amount of drying you do by putting it through a fluidized bed. Often what comes out of a fluidized bed is hot material that can have flow problems themselves if they're allowed to settle, and so often you'll have a fluidized bed dryer followed by a fluidized bed cooler, and I've used these many times with agglomeration, particularly for detergent particles. So we'd have a fluidized bed dryer, and then we'd follow that with a cooler, where instead of pumping hot air in, we pump cold air in order to cool the particles. And again, they're very efficient, and it's used then to give a nice, crisp, free-flowing product. This ability to move the particles around also gives us the opportunity to coat. So as well as fluidizing and moving the particles around, what you can do is to spray a solution onto the particles, and with good control of the spray conditions, you can get the liquid to coat the surface of the particles. And typically you would use a film forming polymer solution that spreads around the surface, and as it spreads you provide hot air into the fluid bed, and that dries the liquid and forms a solid polymer film around the surface. So it's used a lot for protecting particles and also for coating them for controlled release. You can use the same process or the same idea, but instead of having a fairly dilute polymer solution, if the liquid you're spraying on is quite viscous and doesn't have the chance to spread around the particles, then before it dries, then as the particles come together with the sticky surface of the liquid on top of them, they'll stick together and they'll start to agglomerate. And you can control the degree of agglomeration by the process conditions, how fast you move the particles and how fast you move and the amount of spray on that you put on. The density of these agglomerates tends to be very low because they're hitting each other but under quite low shear conditions. And you end up with particles that look more like a raspberry than a compressed agglomerate. And this process is used to grow particle size, as Jim mentioned, from fluidized beds, and is used to instantize food products such as coffee and milk powders by growing the particles and making them slower to wet and dissolve. So it allows the particles to be dispersed in the liquid before they dissolve. Moving on, here's a description that you've seen before from Jim. It just gives you an idea as to why fluidized beds are often used as additional dryers. You can see that often it's difficult to get the very last part of a solvent out of the core of a particle by the time it's reached the bottom of the spray dryer. This can be this is not a problem in lots of instances with spray drying, but it can be in certain circumstances, particularly when you realize that after the particle comes out of the dryer and starts to age, that liquid in the center starts to redisperse, and under some conditions that liquid can diffuse out and back to the surface and make the surface quite sticky, which is not to be desired. Or if you're looking to dry formulations very dry for stability reasons, you want to have as lower moisture active water content as possible. So you put it through a fluidized bed, drying it slowly, low temperature, to give the time for that water or that solvent in the center to diffuse out and to be dried off. And so that's one of the reasons why you'll often see fluidized beds at the back end of a spray drying tower. The next slide is just a quick picture of what happens when you hit the particles with a liquid. You can see in example A, the liquid hits the droplet and starts to spread and as it spreads, it dries, and particularly if you've got a particular polymer that is not sticky as it dries, then you'll form a nice film over time as that liquid spreads. Interestingly, it also shows that with fluidized beds, these particles, as they move around, need to be hit in different places by the liquid in order to get a consistent coat around the surface. And that's why this movement within a fluidized bed is very useful. By contrast, on the right-hand side, you've got a particle where the liquid is very viscous, tends to be sticky, and it doesn't spread very well, and consequently, by the time that particle with that blob on hits another particle, then there's a chance for those two particles to be glued together and start to form the agglomerate. So lots of interesting things you can do there. Important to say that you're actually starting off with the core particle having a particular structure on its own. So fluidized beds is a way of adding structure to an already existing particle structure. Here's a typical example of a coater. Fluidized beds can come in various different shapes and sizes. They can be batch or continuous. The batch processes tend to be circular in cross-section, as shown here. Continuous tend to be rectangular, and some of them can be quite long and thin. So it gives you a lot more control over the particle flows through the bed. So here is the gold standard for coating in industry, the Wurster coater. It's a batch process, and you can see the outside wall shown at the top, and it also has another cylinder in the middle. What happens then is the unit is charged with powder, and the hot air enters the center of that bed with a fairly large hole and a large velocity. It pushes the particles up through the center of that bed, and as it pushes it up, you spray your coating solution into that highly fluidized bed. The particles then will get hit by liquid droplets on part of their surface. They will move to the top. As they come out of that center core, the area, cross-sectional area, is bigger, and therefore the air velocity is lower, and therefore the particles drop down the side, and then they'll get, as they come down to the bottom, they'll get picked up again by the high velocity in the center and get blown up again through the center. So these particles will go around many times during the process, and each time they go through, they'll get hit with a liquid drop which will coat part of the surface, and over time you get a very nice reasonably even distribution. On the left hand side you can see two particles. One is a particle which we've actually made and sliced, and if you look closely you can see a very thin layer of polymer around the outside where it's dried. You can also see, bearing in mind Jim's comments about shape, etc., fluid beds tend to maintain the shape of the particles that they put in. They're compared to fluid with spray drying, where you can actually control the shape by formulation and process conditions. But you're starting off with a solid, it's difficult to change the shape. At the bottom, just for a bit of fun, we've taken a core and we've sprayed it with different inorganic salt solutions and dried them. We've put in a particular different dye to show you that you can get many different layers of coating on these particles to give you different properties. So you could have a core particle, and this is sometimes used by the pharma people. You have a core inner particle, you will spray your particular active ingredient to form a coating on that, and then you can spray another coating on top of that, which would probably be an enteric or controlled release coating to allow you to deliver the active ingredient at the right place and the right time. So on the next slide, you can see that we've got lots of possibilities for engineering particles using fluid beds. You can create additional structure onto an existing structure. You could even, if you wanted, use a solution, an emulsion to spray onto the surface of which would include microencapsulates, and therefore you could have a core particle structure, and then you could put another different structure on top of that, and then you could put a coating on top of that. That ability to keep the particles inside of the bed for long periods of time gives you lots of possibilities for playing lots of tunes on the process. So you can enhance the structure of spray dried particles as well as just drying and cooling. And consequently, it's often used to make particles more free flowing. So you can put a crisp coating on top of a sticky particle and make it crisp and free flowing. You can also control the stability of ingredients by coating them with materials which are such as fats and other polymers to protect them from water ingress during storage. And within that, you can also, by changing the material properties of the solution that you spray on, you can increase stability, but you also control the release rate of these things. However, there are some limitations, as with everything. Particles need to be free-flowing, so it's harder to have fluidized beds with lots of sticky particles. That's not to say that you can't manage these situations. It just becomes more challenging, and you'll sometimes see fluidized beds with vibrating plates on the outside to give the particles that extra kick to break any bonds that they form in the fluidized bed. So one way of handling sticky particles. The particle properties are very important in a fluidized bed, and that can determine how easy that they can fluidize and be processed. If they're too fine, then it's difficult to keep them in the bed, and it's difficult to get that control on the porosity of the bed, so they behave a bit like dust. There are ways around it, just like with anything, but you are getting to the limits of fluidized beds. If the particles are too heavy, which is particularly so as they grow if they become very big in size, it's difficult to get the air to flow fast enough to lift the particles. And so you often get very high flow rates with heavy particles, and it makes things harder but not impossible. And then finally, if the particles are too fragile, the movement within the bed has to be carefully controlled, because what you don't want is to fracture the particles or to erode the surfaces and create fine dusts. Because those particles are going to collide, you need to be careful about breaking the particles up. So you can see there are lots of tunes you can play with fluidized beds, and what those tunes are and the formulations you can put through them depend on what you want to produce and how you want to go to produce it. So, as I said before, both processes benefit from having very high heat and mass transfer rates, because you're making either liquid small droplets or small particles inside a fluidized bed. Spray drying is very fast because basically the droplets fall down into gravity, and this has many opportunities for quick drying, particularly with materials that have very high water content. Fluidized beds, you can have a much longer process residence time, and this can provide the opportunity to give you other structures. So there's benefits for each of them. What you choose depends on what you want to make and the materials that you start off with. Both of those processes, you can have a big impact by the design of your equipment and how you run your process.
Thank you, David, for that overview of fluid bed processing and particle engineering. We just wanted to let you know, as we've concluded the main part of the webinar, before the question and answer session, about 2 more opportunities to learn a little bit more about these processes. And the first of those is at the end of March, start of April, 3-day course run by the University of Leeds, covering spray drying and atomization of formulations. You can see the details there. There's a web link. I'll just briefly mention the fact we start with the basics of the science and lab demonstrations. We move on to industrial formulation case studies and some more lab demonstrations on day 3, talking more about finishing of powders and modelling and future developments. So a highly interactive course, plenty of opportunities to interact with the lecturers, and is always highly rated by the attendees. We've been running that for a number of years now. And the second opportunity is on fluid bed processing and formulation in May. Again, you'll see the web link there. We concentrate in a very similar format, first of all on day 1 on basic science and understanding, including lab demonstrations, moving on to applications and real industrial case studies. And we've got a good mix in both courses, actually, of industrialists and academics. So there's really good grounding both in the science and the practical applications. And on day 3, moving on to some further case studies and new developments in fluid bed processing. So 2 opportunities there, details on those web links and from ourselves with the email address if that's of interest to you. So now we're going to give you the opportunity, and thank you very much for your attention today, and thank you very much once again, David, for your contribution. We're going to give you the opportunity now for any questions, and I see we do have one here. So here's a question, and I think it's a fluid bed question for you, David. I'm just going to unmute you, and the question here, move back to the question from Sharma, is can we make uniform particle shape, particles of uniform shape using fluidized bed drying, David?
No. You can't take an oval particle and make it into a sphere because of that. You can actually, so a lot depends on the shape of the starting material. You can, if you are willing to agglomerate, then build up agglomerate particles of a similar shape and size. Yes, you can do that, but it's difficult if you've got a non-spherical particle and a range of different particles in the fluidized bed to make them all the same. The only way of making them the same is to build them up to an agglomerate which has similar shapes and sizes.
Okay, thank you very much again, and I think that's all we have time for today. So thank you very much for your attention today, and as usual, we will send you within a day or so details of how to access the recording of this webinar, as well as to download the slides. Any other information you can get from us via the email info@iformulate.biz, and information is also on our webinar, on our website about training and webinars. So thanks very much for your attention today, and goodbye, and we hope to see you again. Thank you. Bye-bye.